All right, so welcome back. I want to start by just reminding everybody, and I'll post this later today on Blackboard. We're going to have an extra class, makeup class tomorrow at 3 o'clock. Okay. If you can't make it, it'll be recorded and I'll post it on Blackboard. Okay. Also, the two final quizzes, quiz 4 and quiz 5, are also now on Blackboard. Will it be new material? Well, let's see what we get through today, and then most likely it'll just be review stuff. Okay. But let's see what we finish today. All right. So as I was saying, the two quizzes are also on Blackboard. I think I made them due on Sunday. Yeah, no, it'll be from 3 to 4:15. Okay. Tomorrow's class. All right. Any other questions about that? Okay. The quizzes are on Blackboard. You can do them whenever you like, but they are due on Sunday. Okay, and they will be timed. So once you start each one, you have to finish it in one sitting. Okay. All right. So any other questions about that, or the extra class tomorrow, or the quizzes, or anything else? When is the final? I'll post that on Blackboard as well. You should be able to find it on CUNY first. Okay. When did we say the date for the final is? Give me a second. Let me look it up again. The 16th. Let me just double check. That sounds right. I want to make sure. Okay, yeah. It's going to be 1 week from today, Wednesday, December the 16th, from 4 to 6 p.m. Okay, and it'll be on this link. Okay. Okay, so it's going to be from 4 to 6 o'clock, 4 to 6 p.m. Okay. Yes. A couple of questions about the final. Number one, since somebody asked, since the final is not cumulative, will it be about the same number of questions as previous exams? Yes, that's correct. So it'll be same format as the previous exams, roughly about the same number of questions. And it will be on chapters 4, 5, and whatever we get to in chapter 6 today, okay, and possibly tomorrow. Is the final the same as class time? No, it's going to be from 4 to 6. It'll be 2 hours. Is it possible to make the final after next week? No, I'm sorry. That date is set for us, and I can't change it. The paper is going to be due on the 16th. Yes, that is correct. The paper will be due at that day. The writing assignment is due on the 16th, Wednesday the 16th, 1 week from today. It's 2 hours. Does that mean it's longer? It's not going to be, if it is longer, it won't be by much. It'll be about the same number of questions. Okay. All right. Any other questions? Okay. Did I get your email? Yes, Shoya, I believe I did get your email. I'll take a look and I'll get back to you when I have a chance. No problem. Is there a chance you can submit the essay on Friday? Try to get the essay to me on Wednesday, and then, like I said, if you have an issue for some reason, just send me an email and let me know, and then we'll see if we can work out something. Okay. Okay. Any other questions? All right. So if you have any homework questions, I'm going to ask that you wait till tomorrow to ask them. All right. Right now, I want to move on to chapter 6. Okay. All right. So we are done with chapter 5. We did induction and strong induction. I want to now start chapter 6. So chapter 6 deals with counting and counting techniques. All right. Counting is used in a couple of different areas in mathematics. One of the most important areas, yeah, we're going to start with section 6.1. Okay. One of the most important areas that counting is important is in probability. Probability was originally developed for gambling, but it's important for probability because in probability you need to be able to count outcomes, total number of outcomes. Okay. All right, so we're going to start here with section 6.1, which deals with the basics of counting. All right, so we're going to discuss a couple of counting rules in this chapter. Some of these you may have seen before in some form or another. We're going to start with a rule called the product rule. Okay, so I'm going to write out what this rule is, and then I will give you some examples of where you would use it to count. Okay. All right. Okay. By the way, the branch of mathematics that deals with counting is called combinatorics. All right. And combinatorics has two main branches: enumerative combinatorics and graph theory. If anyone is familiar with any of those. Okay. So maybe I'll just put that in parentheses here. Combinatorics. Okay, so like I said, that has two branches. That's enumerative combinatorics and graph theory. Okay, all right. All right. So the product rule. All right. That was just a side point. The product rule. So the product rule is as follows. Suppose that a procedure can be broken down into a sequence of two tasks. Now, for this rule, we're going to start by discussing when a sequence with only two tasks, but the product rule applies for any number of tasks. So if it's broken down into 2, 3, 4, 5, however many you want. Okay. All right. So if there are n1 ways to do the first task, okay, right? For example, let's say there's 7 different ways you could do the first task. Okay, so n1 would be 7. And for each of these ways of doing the first task, there are n2 ways to do the second task. Okay. Then there are n1 times n2 ways to do the procedure. Okay, so there's some procedure that you need to do. Okay, there's something that has to be done. All right, and it can be broken down into two tasks. Okay, so if there's n1 ways to do the first task and n2 ways to do the second task, then how many different ways can I do the procedure? It's n1 times n2. It's a product, which is why it's called the product rule. Okay. So where would we use something like this? Let's do a very basic example. Okay. Let's say John John has 3 pairs of pants and 7 shirts. How many different outfits can he make? Or can he choose from? Can he make using 1 pair of pants and 1 shirt? Okay, so he's got to make an outfit. That's the procedure here. The procedure is making an outfit or choosing an outfit, choosing what he's going to wear today. Okay. The first task would be choosing a pair of pants. Okay, so the procedure here, is making an outfit. Okay. That can be broken, in this example, that's broken down into 2 tasks. Task 1, picking a pair of pants. Task 2, picking a shirt. Task 2 is picking a shirt. Okay. How many ways can he do task 1? How many choices does he have for task 1? Well, he can do task 1 in one of 3 ways. Why? Because he has 3 different pairs of pants. So there's 3 choices he can make. So task 1 can be done in one of 3 ways. So N1 is 3. Okay. How many ways can he do task 2? There are 7 ways he can do task 2 because there are 7 different shirts he has, so there are 7 different choices he could make, okay? So N2 here is 7. So how many different ways can he make an outfit? It's N1 times N2. That's 7 times 3, well, 3 times 7, which is 21. Okay, so he's got 21 possible outfits that he can make. Okay. All right, so that's the idea behind the product rule. Okay, so any questions on the product rule? Okay. Once we have the product rule, now we can expand it. As I mentioned this before, we can expand it to more than 2 tasks. We can expand it to any number of tasks that we want. So, for example, I could ask you how many different 7-digit telephone numbers can you make? Let's call this part A. Okay. How many different 7-digit telephone numbers can you make? Okay. So here, the procedure is making a telephone number that's 7 digits long. Okay. That is going to consist of 7 tasks. All right. The first task is picking what number you want to be in the first digit. The second task would be picking the second digit. The third task would be choosing the third digit, and so on and so forth. So in this problem, we expand. Or let me write it this way. We can expand the product rule to more than 2 tasks. Okay. So here, there are 7 tasks. Okay. The first task, as I said, is going to be choosing the first digit. So let me draw a little bit of a picture here to help us visualize this. So it's a 7-digit telephone number, 1, 2, 3, 4, 5, 6, 7. Okay. Task number 1 is choosing the first digit. Okay, so task 1 is choosing the first digit. Okay. Task 2 will be choosing the second digit, and so on and so forth. Task 2 is choosing the second digit, and so on and so forth, all the way down to task 7. Task 7. Okay. Can we use n factorial, and can I scroll up? So we'll get to factorials in a minute. Okay. Well, hopefully we'll get to factorials. I can scroll up, yeah. Let me scroll up here for a moment. Okay, is that good? Bit more? Sure. How's that? Okay, good. All right, I'll just leave it for a moment, and I'm gonna scroll back down. Okay. All right. So as I was saying, I'm gonna scroll back down in a moment. But as I was saying, there are 7 tasks here. So our first task is we have to see how many ways we can pick the first digit. Okay. So how many choices do we have for the first digit in this telephone number? How many choices do we have for the first digit? Okay. Let me scroll back down one moment. Okay. So here's the first digit. Let me circle it. Okay. How many choices of numbers do I have that I can put there? Okay. So let me see what you guys say. A couple of people said 7, a couple of people said 10, right? 10 is the correct answer here. There are 10 choices that I have for the number that I can put in this position, right? What are those choices? The digits 0 through 9, okay? So in this particular problem, N1 is 10, because I have 10 choices, right? The 10 digits, 0 through 9. That gives me 10 choices, okay? N2 would also be 10, because for the second digit, I also have 10 choices. Again, the digits 0 through 9. There's 10 different choices that I have, okay? So there's 10 different ways I can do it. So it's 10 times 10 times 10 times 10, 7 times. So this is 10 to the power of 7. Okay. All right, so there's 10 ways I could do the first task, 10 ways I could do the second, and so on and so forth. Okay, yes, for hexadecimal it would be different, yes. Okay. Yeah, okay, good. Okay, so I hope everyone who that said 7 understands now why it's 10. Okay. All right, this was part A. Part B. Yeah, so again, the 7 is the number of tasks that I'm doing. All right, but for each task, how many options do I have? Meaning for the first digit, how many choices do I have to put in the first digit? So it could be the first digit in the phone number could be a 0, could be a 1, 2, 3, 4, 5, 6, 7, 8, or 9. So that's 10 choices. Okay, so I've got 10 choices, 10 ways to pick the first digit. Same thing for the second task, which would be picking the second digit. I've got 10 choices for that, one of the numbers 0 through 9, and so on and so forth for each of them. Okay. Okay. Part B. So in part A, I have the same number of choices for each task, okay? I could give you a problem where each one changes, all right? So for example, let me give you a problem like this. Let's say same problem, but how many telephone numbers, again, it's 7-digit telephone numbers, 7-digit telephone numbers can we make if the first digit cannot be 0 or 1. Okay, so the first digit can't be a 0 or a 1. So how many telephone numbers can we make now? So again, we still have 7 tasks here because we got to pick 7 numbers. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right. So this would be N1, N2, N3, N4, N5, N6, N7. Okay. How many choices do we have for the first digit? Okay. Yeah, that's right. Okay, but let's go through it. Okay. How many choices do I have for the first digit? Okay, I can't use a 0 for the first digit, and I can't use a 1. So I'm left with how many choices? I had 10 choices, but I can't use 2 of them, so I'm left with only 8. Okay, so how many ways can I do the first task? There's 8 ways. There's 8 choices for the first digit. Okay. Let's move on to the second one now. For the second digit, how many choices do I have? Okay, so the second digit, there's no restriction on that. It can be any number. So I've got 10 choices. Okay, any of the numbers 0 through 9, right? 0 and 1 are back in. And same for the rest. Again, I have 10 choices for all the rest. So as you said, now my answer is 8 times 10 to the power of 6. Okay, I'll leave it like that. All right. Okay, now part C. Okay. Let me modify this again a little bit. So again, how many 7-digit telephone numbers can we make if the first digit can't be 0 or 1? So that's the same, okay? But also, let's say I tell you that and no digit can repeat. Okay, so I can't. No number can repeat. So if in my phone number I use the number 7, or let's say 9. If in my phone number I've used the number 9, 9 can only appear once. All right, I can't use 9 again. Okay, so each digit is only allowed to appear once. There is no repeating number allowed. Okay, so again, it's still 7 tasks because it's a 7-digit phone number. 1, 2, 3, 4, 5, 6, 7. Okay, again, N1 through N7, right? N1, N2, N3, all the way up to N7. Okay, so again, how many choices do I have? Yeah. Mhm. These are all different parts of one example. If you want, you can think of them as 3 different examples. It's fine. All right, so again, how many choices, again, do I have for the first task, for the first digit here? Again, it's 8, right? Because I can't use a 0 or a 1. Now, let me ask you, how many choices do I have for the second digit? Yeah, that's right. It's 9. Okay, why 9? Because normally I have 10 choices, but whatever I used for N1 in that position, I'm no longer allowed to use that number anymore. So take that one out, whatever number that was, I'm left with 9 choices. So there are 9 choices available to me. All right, how many ways do I have to pick N3? How many choices do I have for the third digit? 8, right? And again, why 8? Because I've used 2 numbers. I'm not allowed to use those numbers again. So that leaves me with 8 choices. Okay, the numbers 0 through 9, and just take out whatever 2 numbers I've used. So N4, how many choices do I have for that? 7, right? And then for the next 6, then 5, then 4. So this is what my answer would be. 8 times 9, 8, 7, 6, 5, 4. Okay, whatever that equals to. Okay, you could leave it like that, or if you wanted to plug it into a calculator, you could do that either way. Okay. All right, so any questions on the product rule? Okay, and then there's many different variations we could do with the product rule. You could see examples. I'll give you some homework problems. You could see examples with initials, people's initials, with license plates, and things like that. Okay. Okay, so it's 483,840. Thank you. Thank you for checking that out. Okay. Okay. All right. So that is the product rule. All right, and then like as I said, there's many different types of problems that could use the product rule, that make use of the product rule, and you could get a little bit more complicated, but this is the basic idea. So let's now move on to the next rule for counting, the sum rule. All right. So the sum rule is also a very basic rule. I'll write it down and then I'll show you an example, and hopefully you'll see it. It sort of makes sense. It's pretty straightforward. All right. So the sum rule is as follows: if a task, so a single task, if a single task, all right, and I'm not writing the word single. But I'm just emphasizing. So if a task can be done either in one of n1 ways, or in one of n2 ways, where none of the set of n1 ways is the same as any of the set of n2 ways, okay, so there's no overlap between them, right? There's no overlap. There's no if I was to put it in terms of set theory, their intersection would be the empty set. Okay, so where none of the set of n1 ways is the same as any of the set of n2 ways, then there are n1 plus n2 ways to do the task. Okay, and that's why it's called the sum rule. Okay. All right, so if I have some task I have to do, I could either do it in one of n1 ways or one of n2 ways, right? So I could do it in one of, let's say, 7 ways. Let's say n1 is 7, or n2 would be 10 ways. Then the total number of ways I could do the task would be to just add them up, and that would give me, in my example, 17. Okay, let me give you an example. Let's say Molly wants to go on vacation from New York City to Miami. Okay. She can go by taking one of, let's say, 7 flights. Okay, she has 7 options for the planes she can take, or by taking one of 3 trains. Okay. So right, she goes on Google. She says, how can I go to Miami? So she sees, oh, tomorrow there's 7 different flights or 3 trains that are going to Miami. Okay. So in how many ways can Molly get to Miami? We have a question. Is this kind of like probability? This is used in probability, yeah. I mentioned this before. Counting is used in probability. I'm not just in probability, but it's very important in probability because you need to be able to count total number of outcomes in probability. So, all right. So these are very basic rules for counting. Okay. And so in how many ways can Molly get to Miami? All right. So the task is getting to Miami, right? All right, it's a single task. All right. She can do it in one of n1 ways. So n1 here, the first way of doing the task would be to go by plane, right? So flying. So if she flies, how many ways can she get to Miami by flying? She could do it in one of 7 ways, okay? If she goes by train, and how many ways can she get to Miami by train? She can go in one of 3 ways. Okay, so the total would be n1 plus n2, that's 7 plus 3, which is 10. So she's got a total of 10 ways that she can get to Miami. Okay, so that is the sum rule. Any questions on that? Are there keywords like and or? No, I wouldn't say that there are keywords like and or. You just have to sort of realize it. Am I doing a single task and there's just two different sets of ways I can do that task? Okay. Should we use words like task? No, you don't have to use you don't have to actually use the words task or procedure. I'm just sort of using those words in the definitions here. Okay. So how do I know? How do you know if if a problem requires you to use the product rule or the sum rule? All right. So just briefly, for the sum rule, if it's a single thing that you're trying to do, it's one thing, one task, okay, and you just have two different ways or three different ways that the sum rule could be applied to more than just two options, okay. If you've got two or three or four different ways you could do that same task, so then you just add them all up to get the total, okay. If you have a procedure, so you mean you have to do a bunch of tasks, okay, one after the other, let's say, then you're gonna have to use the product rule. Okay, so it's a bunch of different things that you want to do, product rule. If it's one thing that you want to do, you just have different ways that you can do it, that would be the sum rule. Okay. Okay, so hopefully that will help. Yeah. All right, and this is basically, if you read the definition, that's what I wrote in the definitions here for the product and the sum rule. Okay, so let me write that again. Sum rule is one task that can be done in different ways. Product rule is a procedure that requires you to do several tasks. Right, and usually for the product rule, it's a several tasks that you have to do one after the other. Okay, you have to do this first, then this, then this, then this. Okay. Sure. Okay. Okay. All right, so those are those rules. Okay. Let's now discuss, I want to discuss one more rule for the basic counting rules, okay, the subtraction rule. All right, the subtraction rule is as follows, okay. So here, this is, remember in the sum rule, which I'm going to scroll back up for a minute here. And when I described the sum rule here, I specifically wrote down where none of the set of n1 ways is the same as any of the set of n2 ways. Okay. So the question now is, what happens if there is an overlap? Okay. Some of the n1 ways are the same as some of the n2 ways. Okay. When that happens, if you add n1 plus n2, you're going to be counting those ways twice. Right? It's like you're counting the intersection twice. So in order not to count them twice, you have to subtract those number of ways off once. Okay, so that's going to be the subtraction rule. All right, so let me write that down. Okay, so if a task can be done in either n1 ways or n2 ways, then the number of ways to do the task is n1 plus n2 minus the number of ways to do the task that are common to the two different ways. Okay, so if you want to think about this in terms of set theory, right, if you go back to set theory, okay, so let's say I have some set A and some set B, okay. All right, so I want to, by the number, N1 would be the cardinality of A here, okay? N2 would be the cardinality of B, and then their intersection would be in the middle, okay? So if I want to count how many ways I can do A, how many ways I can do B, if I just add A plus B, I'm going to count the intersection, these two here, I'm going to count them twice, okay? So in order not, so in order to make sure I don't count them twice, I have to subtract that intersection off once, okay? That's the idea. By the way, the subtraction rule is also called the principle of inclusion-exclusion. Okay, the principle of inclusion-exclusion. Okay. Okay. Right. So if I were to write this out using set theory notation, I would be that the cardinality of the union of A and B, right? If I want to add the total number of ways I can do A with the total number of ways I can do B, that would be equal to the cardinality of A plus the cardinality of B. But then I'm counting the intersection twice, so I have to subtract off the cardinality of the intersection. Okay, so that's just this rule written using set theory notation. Okay, let me give you an example of this. Okay, let's say a computer company receives 350 applications from computer graduates for a job. Suppose that 220 of these applicants majored in computer science, 147 majored in business, and 51 majored in both computer science and business. Okay, so the question is, how many of these applicants majored neither in computer science nor in business? Okay. All right, so there's a total of 350 applicants. Okay, now if you add 220 plus 147 plus 51, you have a problem. Okay, those 51 people that are majored in both computer science and business, they've already been counted. Okay, they're counted in the 220 and the 147. All right. So when I said that 220 of these applicants majored in computer science, I don't mean that they just majored only in computer science. I mean they majored in computer science, and some of them may have also majored in business. Okay. 147 majored in business. Some of them may also have majored in computer science. How many total majored in both? 51. Okay. So if you want to, again, think of it as set theory, okay? Here, this first circle represents the computer science majors. This one represents the business majors. So the total in the middle is 51. The intersection is 51. Okay. So we have an answer already. Okay. Okay. So let's see. Altogether, how many computer science majors were there? So the total number of computer science majors is 220. The total number of business majors is 147. And the intersection of computer science and business is 51. So using the subtraction rule, or the rule of inclusion-exclusion, the total number of computer science and business majors is going to be 220 plus 147 minus 51. Okay, I'm subtracting off the intersection. Okay, I'm just using this here. Okay, so that's N1 plus N2 minus their intersection, minus the common ways. Okay, which gives me 316. So of the applicants, 316 were either computer science majors, business majors, or both. Okay, so 316 applicants were either CS majors, business majors, or both. So how many were neither? Well, there was a total of 350 minus 316. How many were neither? The answer is 34, as you said. Who said it? It was Shakir? Yeah. Okay. So 34 were neither business nor computer science. Okay. All right. Any final questions on that? Okay. So that's the subtraction rule, or the principle of inclusion-exclusion. Okay. There is one more basic counting rule that's discussed in this chapter called the division rule, but for the sake of time, I am going to skip it. Okay, so we have three basic rules: the product rule, the sum rule, the subtraction rule. We will stop there for 6.1. Okay. 6.2, I'm going to skip over. 6.2 is the pigeonhole principle. I mean, if you want, I can do the pigeonhole principle in about 10 seconds. Okay, you ready? Here we go. No, thanks. I'll do it in 10 seconds. I'm not going to do it. I'm just, so to speak, I'm joking a little bit. But the basic idea is the pigeonhole principle is as follows. If you have, let's say you have 10 boxes and you have 11 objects, okay? Then you want to put those objects into the boxes. At least one box has to have more than one item in it. Okay, should I say that again? You have 10 boxes, you have 11 items. You want to put all your items into the boxes, then at least one of the boxes has to have more than one item in it. That's the pigeonhole principle. All right, we're not really doing it. We're going to skip over it. Let's move on to 6.3. Okay.
So aren't we gonna do this division rule?
The division rule we're not doing either. So we're not doing the division rule, and we're not doing the pigeonhole principle. We're skipping those two.
This won't be an exam.
No, the pigeonhole principle will not be on the exam. Okay.
All right. Thank you.
No problem. Okay. I'm moving now to 6.3. 6.3 deals with, where did 220 come from? Oh, let me go back to that example. I'm sorry. 220 was given to us in the question, in the problem. Right. 220 were computer science majors, okay? 147 were the business majors, and 51 were the ones that were both. So that 51 was the intersection. Okay. All right. Okay. All right. So 6.3 deals with permutations and combinations. Okay. So let's see how far we can get with that today. I may have to do a little bit more of this. I may have to finish this up tomorrow during our extra class. All right. We're just going to define what permutations and what combinations are and how to calculate them. Okay, so I'm sure many of you have heard of permutations and combinations before. You've probably seen it in some. Can we stay later today? Okay, let's see how far we get. Okay, let's see how much time we have. All right. I'm sure many of you have seen combinations and permutations before. Just in the chat, just let me know are you familiar with permutations and combinations? Does anyone here remember seeing those terms before? Okay, so some of you have, a lot of you haven't. That's fine. Okay. Let's start with permutations. Okay, we're going to define what that is. Okay, and the goal in this chapter is I'm going to define what a permutation is, and then we're going to discuss how to count the total number of permutations of something, usually of a set. Okay, then I'm going to define what a combination is, and then we're going to discuss how to count the total number of combinations of, let's say, of a set. Okay, of a certain number of objects. Okay. All right, so what is a permutation? Okay, so definition. A permutation of a set of distinct objects is an ordered arrangement I'm underlining ordered. That's important. A permutation, this is really the key difference between permutation and combination. A permutation is an ordered arrangement. A combination is a set where order doesn't matter. Okay, so a permutation of a set of distinct objects is an ordered arrangement of those objects. Okay. An ordered arrangement of R elements of a set, is called an R permutation. Okay. All right, so for example, let's say, well, let me give you the example first of a regular permutation. Okay. All right, so let's say I have a set with 3 letters, C, A, and T. Okay. Question: how many permutations are there of the letters C, A, and T? Okay, so a permutation is just an arrangement. So if I'm asking you how many permutations can I make using these 3 letters, I'm asking you how many different ways can I arrange these letters into some order? How many different arrangements can I make? So one permutation, let me write them out. It's a small set, so I can write them all out. One permutation would be to write CAT. That is one permutation. It's one arrangement. All right. What's another permutation? Another permutation would be CTA. Okay, that's a different arrangement. It's a different order. Okay. A third permutation would be TAC. a fourth TCA, a fifth ACT, and a sixth ATC. Okay, and that's all of them. There are no others. Okay, so altogether, if I've got a set of 3 distinct objects, in this case, the letter C18, how many permutations are there? How many arrangements can I make using those objects? The answer is 6. So there are 6 permutations. Okay, using those 3 letters. Okay, let's call that part A. Part B. How many, let's say I ask you how many 2 permutations are there of the letters C, A, and T? Okay, so here, this is an R permutation where R is 2. So what does that mean? What is a 2 permutation? A 2 permutation means I'm only allowed to use 2 out of the 3 objects. I'm only allowed to use 2 of the objects. Okay, so how many arrangements can I make if I'm only allowed to use 2 of the letters C, A, and T? Okay, well, one 2 permutation would be CA. Another would be AC. Okay, what would be another 2 permutation that I could make from this set? What do you guys say? Give me some choice possibilities. AT, TA, good, and what else? Anything else? Is that it? Okay. There's AT, TA, and yeah, there is CT, TC. Okay. Yeah. So in total, how many 2 permutations can I make? The answer in this example happens to again be 6. They won't always be the same though. Okay, so there are 6 possible 2 permutations. Okay. All right, let's say part C. What if I ask you how many 1 permutations are there using those letters? How many 1 permutations? Okay, well, 1 permutation means I'm only using 1 object from the 3. So A, that would be 1 possibility. C, that would be another possibility, and T would be another. So altogether, there are 3 possible 1 permutations. Yeah, very good. All right, so that's the idea of permutations, okay? There is a formula for permutations, and there's also a notation for it, okay? All right, so let me give you the formula for the total number of R permutations. All right, so this is a theorem. All right, so if n is a positive integer, and R is an integer, with R greater than or equal to 1, less than or equal to n, then there are so the notation we use for permutations is P of n comma R. Okay, so P of n comma R is the total number of permutations that we can make, total number of R permutations we can make from a set with n objects. Okay, so the set is a total of n objects, and this is asking you how many R permutations can you make. Okay, so this is equal to, all right, n factorial. Somebody had asked about factorials before. This is where they come into play. It's equal to n factorial over n minus R factorial. Okay. So there are this many R permutations of a set with n distinct elements. Okay, so this is the formula. Make sure you know this formula for a total number of R permutations. Yes. So somebody asked in the comments. Sometimes there's different notations that are used. So sometimes it's written as p of n comma r. Sometimes it's written as npr, where n and r are subscripts. Okay, that's npr is the total number of R permutations. That's not National Public Radio. Okay. Yeah, so you can use that notation too if you like. Okay, so again, p of n comma r means the total number of R permutations you can make from a set of n distinct objects. Okay, how many different ways can I make an arrangement of R objects from a set of n? Okay, so for example, let's say I ask you to evaluate p of, let's say, 8 comma 3. Okay, in other words, I'm asking you how many 3 permutations can you make from a set with 8 distinct objects. So p of 8 comma 3, using this formula, which make sure you know, make sure you memorize it. Okay, that's equal to n here is 8 and r is 3. N is 8, r is 3. So that's going to be 8 factorial over 8 minus 3 factorial. That's 8 factorial over 5 factorial, which is equal to what? Well, 8 factorial is, hopefully you remember. Oh, the formula for total number of permutations. That's the one you should memorize. Okay. P of n comma r. Okay. All right. So what is this thing equal to? 8 factorial, remember, is 8 times 7 times 6 times 5 times 4, 3, 2, 1. Okay. 5 factorial is 5 times 4 times 3 times 2 times 1. So look at that. If we cancel out the things on top with the things on the bottom, the 5 factorial on the bottom will cancel out with the 5 and down on the top. So all I'm left with is 8 times 7 times 6. So this thing actually simplifies nicely, right? Everything in the denominator will cancel out with stuff from the numerator. So 8 times 7 times 6 will be my answer. Whatever that equals to, I'm just going to leave it like that. Okay. And you could plug that into your calculator and get that. Somebody got 336. I think that sounds about right. Okay. All right. So any questions up to this point?
Can we use the, like, what's the difference between product rule and the permutation?
Excellent. That's an excellent point. So thank you for bringing that up. I was going to bring that up. But since you bring it up now, let's discuss it. Hopefully, as you noticed, hopefully, if everyone else takes a moment and thinks about it, this formula for the total number of permutations is really just from the product rule. Okay. Right. If you had thought about this using the product rule, that's really where it comes from. It's based on the product rule. Okay, so you're right. They are basically the same idea. Okay. All right. So they will always cancel out that way. Yeah. Everything in the denominator, when you do this formula for permutations, everything in the denominator will cancel with stuff on the top. Okay. By the way, I also want to remind you guys. Let me make a note of this. Note. 0 factorial. What is 0 factorial equal to? Anyone remember? Yeah, it's equal to 1. Okay, 0 factorial is 1. Okay. Just we just define it that way. Okay, yeah, by definition, we just defined it as 1. Okay. Okay. All right. So we can use permutations also in word problems. Like you see a lot of word problems that ask you the total number of ways to do something or to make an arrangement. Anytime you're asked the total number of ways to make an arrangement or to order something, that's permutations. Okay, so you can use the permutation formula here. So for example, okay, how many ways can a teacher seat 4 students at the front of the class if the class has, let's say, 20 students? Okay. So this problem here, I'm asking you, how many ways can a teacher seat 4 students at the front of the class if the class has 20 students? This problem is actually a permutation problem, okay? I have a set here of 20 objects, the 20 students, right? It's 20 distinct objects, and here is 20. I'm asking you, how many ways can I seat 4 students at the front of the class, okay? And if I switch them around, that's a different arrangement, right? The order matters, right? There's a student who's going to be in the first seat, a student in the second, the third, and the fourth, okay? So there's an arrangement of the 4 students, okay? If I switch them around, that's a different arrangement, okay? So order here matters because there is an arrangement, there is an order, okay? So order matters. So that makes this a permutation problem. Okay. So the question is asking us how many 4 permutations can we make from a set of 20? So here n is 20, r is 4. Okay, so anytime you're given a problem like this, you have to ask yourself, does the order matter? Is there an arrangement? Is there an order? If there is, if logically there is, then it's a permutation problem. Okay, so this is asking us to evaluate p of 20 comma 4. Okay, how many ways can I pick 4 students and then put them in some sort of arrangement at the front of the class? Okay, so using the permutation formula, this would be 20 factorial over 20 minus 4 factorial, which is 20 factorial over 16 factorial. Okay, so on the top, I'm going to get 20 times 19 times 18 times 17 and times 16 dot dot dot. On the bottom, I'm going to get 16 times dot dot dot. Everything from 16 and down will cancel. So I'm left with 20 times 19 times 18 times 17. Okay, whatever that's equal to. I'll just leave it like that. Okay, now, and before somebody was asking about the product rule. If you had wanted to, you could have approached this problem using the product rule as well, instead of using the permutation formula. Okay, because you could have said to yourself, this is a procedure where I have 4 tasks. I've got to pick a student to be in the first seat, pick a student to be in the second, the third, and the fourth. So you could have thought of this as saying, I've got 4 tasks here. How many choices do I have for the first task? Well, I've got 20 choices, 20 ways, because I can pick one of 20 students. Once I pick a student to be in the first seat, there's 19 choices left for the second, 18 left for the third, 17 left for the fourth. Okay, so either way you did this problem, if you use the product rule or you realized its permutations and use the permutation formula, you would arrive at the same answer. Okay, so really you can do it either way. Okay, product rule works. So the product rule works for permutations, and that's really what the formula for the permutations is based on. It's really based on the product rule. Okay. So that is permutations. Okay, any questions on that? Okay, let's do one more example. Okay. How many ways are there to select a first prize winner a second prize winner, and a third prize winner. From 100 different people who have entered a contest. Okay. All right. So because in this problem, because it matters, all right, it matters which person wins which prize, okay? My three prizes here are all distinct from each other. So that means I have to pick a person to win the first prize. Then I have to pick a person to win the second prize. Then I have to win a person to pick the third prize, okay? So they're all distinct from each other. That means that the order matters here, okay? So because it matters which person wins which prize, that means that order matters. Okay, right? For example, it's different if John wins first prize than if John wins second prize, right? That would be a different arrangement. Okay. Yeah. Okay. Yeah. All right. So this in this problem order matters. So again, it's in this problem it's P of 100 comma 3, right? How many 3 permutations can we make out of 100 people? So this is going to be 100 factorial over 100 minus 3 factorial. Okay, which is going to be 100 times 99 times 98 times 97 dot dot dot. On the bottom, 100 minus 3 is 97 factorial, so that's 97 times dot dot dot. The 97 and down will cancel, so as you said, it's 100 times 99 times 98. Okay, and again, if you use the product rule, it's as follows. Using the product rule, you would get the same thing, right? You have 100 choices for the first prize, 99 choices for second prize, 98 choices for the third prize. You would get the same thing. Okay. All right. So any final questions on permutations? Okay. Let's see. Let's start combinations. Let's see if we can finish it today. All right. I might go a couple of minutes over. Let's do combinations. Okay, so as I mentioned before, the difference between combinations and permutations is that permutations is an ordered arrangement. A combination is an unordered collection. So in a combination, order does not matter. Okay, all right. So if I have a set of n objects, all right, and I ask how many R combinations can I make, I'm really asking how many subsets I can make where each subset has R elements. All right, but let me write it down. Okay. All right, so an R combination of elements is an unordered selection unordered selection of R elements of elements of a set. That should be in there, of elements of a set. Sorry, just squeeze those words in there. An R combination of elements of a set is an unordered selection of R elements from the set. Okay, so let me actually also put just in brackets on top here. A combination is an unordered collection of elements. Okay, so a combination is an unordered collection of elements. An R combination of elements of a set is an unordered selection of R elements from the set. Okay, so in other words, like I said, really an R combination is the total number of subsets I can make, where each subset has a cardinality of R, has R distinct objects in it. Yep, this is still 6.3. Okay. All right. Okay. So for example, let's say I have a set, this set from before, CAT. Okay. How many combinations, let me say 3 combinations. How many 3 combinations are there using the letters C, A, and T? Okay. In other words, how many ways can I choose 3 letters from the letter C, A, and T? Okay, there's really only one combination, CAT. Okay, so since the order doesn't matter, let me write it as a set. Since the order doesn't matter, there's only one 3 combination. Okay, this is the same as, remember, order doesn't matter in sets. This is the same as ACT, right? The same as TCA. Okay, and so on and so forth. So there's really only one 3 combination. Okay, there's only one way I can pick 3 elements from here. There's only one way to choose 3 elements from this set. Okay. All right. Let me ask you, how many 2 combinations are there using the letters C, A, and T? Okay. So in other words, how many ways can I pick 2 out of 3 objects here where the order doesn't matter? Okay. So one combination would be the set CA. That's 1 2 combination. Another 2 combination would be AT. And a third would be CT. Okay. All right, so you could think of our combinations as subsets. Okay, so there's only 3. Okay, there's only 3 2 combinations. Okay, there's 3 ways to pick 2 out of the 3 letters where the order that I pick them doesn't really matter. Okay, so CA is the same as AC, AT is the same as TA, CT is the same as TC. Okay, so there are 3 2 combinations. Okay. If I asked you how many 1 combinations there are, what would be the answer from those 3 letters? Yeah, again, the answer would be 3. There are 3 ways that I could pick one object. Okay, I could either pick C, I could pick A, or I could pick T. Okay, so there are 3. 3 1 combinations. Right? Either the letter C, the letter A, or the letter T. Okay, so I'm asking for the total number of combinations. Another way of thinking it is the way I've been saying, that you can think of it as how many ways can I pick or choose R elements from this set where the order of those elements does not matter. Okay. All right. So let me give you the formula for combinations. Okay. And then maybe we'll stop with that. All right. All right. So theorem. I'm just going to give you the formula, and that will be the last thing for today. Okay. So the number of R combinations of a set with n elements Hello? All right. All right, give me 1 second here. Okay. Oh, 1 second, guys. Okay. All right, 1 moment here. Sorry, let me try. Sorry, just 1 moment, guys. 1 second. Okay. Okay, I think we're back. Yeah, we're back. Okay. All right, so let me give you this formula here. The number of R combinations of a set with n elements where n is a non-negative integer. So let me write it this way. N is a natural number. Let me write it better. Sorry. N is a natural. N is a natural number. It's a non-negative integer, and R is an integer with R greater than or equal to 0, less than or equal to n, equals. So the notation uses C of n comma R. That's the total number of combinations of R, or the total number of R combinations of a set with n elements is equal to n factorial over R factorial times n minus R factorial. Okay, so that is the formula. Okay. All right, so let me just show you quickly how to use this formula once. It's very similar to the permutation formula. And by the way, sometimes this is written as NCR, okay? And sometimes it's also written this way. Okay, so that's just a side point. Okay, there are 3 different notations used. Okay. All right, so let's say I asked you what is C of 8 comma 5, the total number of 5 combinations from a total of 8 objects. So how many ways can I choose 5 out of 8 objects where their order does not matter? So that would be 8 factorial over 5 factorial times 8 minus 5 factorial. That's 8 factorial over 5 factorial, 3 factorial, okay, which is equal to 8, 7, 6, 5, 4, 3, 2, 1 over. Now 3 factorial is 3 times 2 times 1 times 5 factorial, which is 5 times 4 times 3 times 2 times 1. So the 5 factorial on the bottom will cancel out with the 5 and down on top. 3 times 2 is 6, so that cancels with the 6 on top. So this is 8 times 7, right, which is 56. Okay, all right. So let's stop with that for today. I'll post this lecture with some homework. You can leave it as 8 times 7. You can write it as 56, either way. Any last minute questions? Let's see. Professor, I have a set question. Is the cardinality of the set, those two sets the same? Yeah. When counting cardinality, we only count distinct elements. So if it appears more than once, we don't count it again more than once. Can you write it the denominator as 15 factorial? The answer is no. Okay, 5 factorial times 3 factorial is not the same as 15 factorial. Okay. All right. Any other questions? All right. Maybe one day. All right. We still have one more lecture. All right. Yeah. So we're gonna still have class tomorrow at 3 o'clock. Okay. It'll be a review. We'll may go over this stuff a little bit more. Maybe I'll do some more combination permutation problems. We'll also discuss tomorrow a little bit again more in depth what will be on the final exam. How many proofs will we need to know for the finals? Well, I'll ask you to do an induction and a strong induction problem. Okay, at least one induction problem and at least one strong induction problem, if not more than that. Tomorrow, will we have some new material to go over? No, I might just do this, go over this again, maybe do some more problems on it. Okay, I might go into it in a little bit more depth, but nothing new. All right. Okay. All right. Thank you, everybody. For everyone that's able to come tomorrow, I'll see you then. If not, I will see you for the final exam. Let's do the attendance. Thanks for staying a few minutes late today. I'll see you tomorrow. If you have any questions, again, you can email me and I'll try and get back to you as soon as possible. Okay. All right. Last call for attendance. Okay, take care, everybody. I'm gonna head out.